I'm going to go through at this point. This will be intended to be quick. I'm not going to go into detail on these studies. I'll just show you kind of a smattering. They're biased towards the terrestrial realm because I'm biased towards the terrestrial realm. But there have been both marine and terrestrial studies. I'm just going to give you show you a smorgasbord of different kinds of applications. So you can see, get a sense for the variety of different questions people are trying to address with this. This is, the pictures here are my lab back at CU Boulder. So this is the new Thermo 253 Plus. This is, as I said, a new innovation. So they had the MAT 253s. Now they're issuing 253 Pluses. And this one has, I think, the first fully dedicated clumped isotopes and CO2 detector. So most of these systems have sort of a universal detector, meaning, oh, I could adjust the magnetic field, move myself over to measure N2O or O2 in addition to CO2. We're not going anywhere with this one. This one has been configured specifically with differences in both the slit width and the slit positioning to be sort of maximize measurements of this range of CO2 isotopologues. It also has 10 to the 13th ohm resistors, so most of these high masses that we measured previously had 10 to the 12th ohm resistors, and this just helps you get a little bit more information out of these really small abundance measurements. So when you actually look at a peak spectra of this on our machine, our mass 47 peak is even higher intensity than mass 46, 44. So again, this is just your resistor talking. And then the other feature that turns out to be pretty helpful with this system are some of the innovations we've made on this end. So we're working with a different inlet system. This is a custom-made CO2 gas generation and cleanup device. You have a carousel over here that drops a sample in, produces CO2 gas. It goes through sort of your normal cryogenic cleanup steps, but we do one additional really forceful cleaning step. We run it through a GC column that's held at about -20, so it just makes the CO2 pass through really, really slowly. And it's packed with pore pack, which has the advantage of resolving CO2 relatively early, and things like various hydrocarbon and halocarbon fragments that would be likely candidates for causing that kind of mass interference or isobaric interference on mass 47 cleans them out. So we're having fun with this. The one other thing we've added on it is a residual gas analyzer. So this is basically a mini mass spec. And we are hoping to use this to help us do a better job of screening for these kinds of isobaric contaminants. Right now, our system for doing this is just sort of a guilt by association metric. And so there are probably occasions where our flag for contamination is causing us to take out samples that we could actually use. And you don't want to lose any when you have to measure one for 3 hours. You don't want to lose anything that you anything you don't have to. And also there are probably occasions where we're getting contaminants and we're not recognizing it. Our sort of flag for contamination isn't going up. So those are things going on in our lab right now. And then this is just kind of a long laundry list of things that this carbonate thermometer has been applied to already. So Paleozoic climate, dinosaur body temperatures, glacial interglacial climate, Cordillera paleoelevations in a number of different tectonic ranges, Cenozoic paleoclimate, things like issues of biogenic effects, so looking at vital effects in bivalves, corals, forams, vertebrates, issues of methanogenesis, carbonate diagenesis, fault carbonates, meteorites. So there's been a lot of applications already. This one, and again, you'll have these slides, so you'll have references to them, so I'm not going to spend very much time. This is just to give you a sense of the smattering. So this is a paper by Brand et al. 2012 using clumped isotopes to kind of look at environmental change associated with the Permo-Triassic extinction. And they argue that indeed there is some kind of temperature warming event that they see crossing that boundary. We have applications in the realm of terrestrial paleoclimate. I'll talk a little, if I have time, I'll talk a little bit more about this, but this is exploiting some of the seasonal bias that we see in carbonate formation, often in soil carbonates, to basically compare to mean annual temperature from leaf fossils and look at the range of seasonality on land during really warm climates in the past, which has been a climatic question. Marina Suarez and others have looked at temperature and O18 change associated with the East Asian monsoon. We've had people who have exploited the fact that we get a nice both temperature gradient and O18 water gradient with elevation, and the fact that you get both of those pieces out of carbonate minerals to go back in time and try and say something about how high mountains were in the past. So I know most of you, how many geologists do we actually have in the room? Yeah, okay, a lot of you. So there's a number of folks probably interested in the paleoclimate side. Tectonically, there are a lot of different models for development of mountain ranges. And one of the best ways we could potentially test those ideas if we actually knew how high a mountain range was at different points in time. And it turns out that's easy to do now, easy-ish, and really hard to do in the past. And most of our approaches for doing this are based on paleo-environmental, paleoclimate data like paleotemperatures and hydrogen and oxygen isotopes. So it's been applied to a number of different settings, particularly in the Western US. Carbonate diagenesis, this opens a lot of realms for taking things like traditional CL cement stratigraphy and looking at different generations of cement and pathways, and actually parsing apart the settings for when carbonate porosity changes, when you get different cementation and recrystallization events. So people have spent time thinking about carbonate diagenesis both from the perspective of learning more about porosity and pore filling changes, so of obvious interest to the oil industry for thinking about when you both fill up the pores that might hold the oil and when you might dissolve out and create more pore space to hold oil. But it's also really important for screening samples for paleoenvironmental work. So a lot of the focus has also been looking at different systems for saying, okay, we have a number of things that petrographically might look pretty well preserved that follow, we'll kind of call these our well-preserved end member. We have things like this secondary spar that we know formed later on, and based on the temperature and the O18 of water, are probably forming from burial fluid. So there's a candidate fluid that's going to come in, interact with your carbonate sample, and potentially recrystallize it, dissolve, or reprecipitate that carbonate and give you a quote-unquote wrong answer. And when we look petrographically at things that look recrystallized, they end up sort of plotting partway through, both in temperature and O18 space. So we can use as much of the information in some of these samples to parse apart some of these things as well and keep ourselves out of trouble in the geologic record. Dinosaur body temperature. So this has been evolving work asking that question, are dinosaurs warm-blooded? Are they cold-blooded? Here you might actually be able to start getting some of that information both from the bioapatite carbonate that exists in enamel, as well as exploiting things like eggshells of different kinds of organisms. And what you see here is it's probably not a simple answer. In this particular example, there are some dinosaur species that end up looking more like modern ectotherms. So those ones would be considered more likely candidates as being cold-blooded versus other organisms that look more like modern birds. So you probably have some dinosaurs that are warm-blooded, some dinosaurs that are cold-blooded, so not a simple answer to that one. And if you're looking for more, there's a lot of different resources. I'm happy to talk to you about some other papers if you're curious. But you can find some good repositories for recent papers at both of these websites, and that should be listed in your handout. Clumpy Wiki. OK, so as you've noticed the recurrent theme, we've all been spending time talking about isotope systems, and then we also talk about the intricacies of the systems we're interested in reconstructing, so that we kind of have a sense for what caveats we're going to have to keep in mind if we're going to apply all of our isotopic tools well. And clumped isotopes is no different. So as I said before, we are really just getting a mineral formation temperature. So one of the big questions that's come up is this issue of when do carbonates form in a variety of different settings. And you can imagine in terrestrial realms, there are, even in marine systems, there are a lot of levers to play with. But the levers in the terrestrial realm on your carbonate system are really big, right? So this is your sort of summary chemical equation of forming carbonates. And we've already been given, of course, the warning that you need to think about the whole kind of carbonate system and all of your carbonate chemistry. Terrestrial realm is no different. What I want to highlight is just remembering is to just bring this back up and kind of think about the different directions you can drive the system if your goal is to get carbonate to form and think about when it forms. So there's an interplay in terms of thinking about what our temperatures might mean based on what levers you can kind of play with to get that carbonate to form. So different settings that might promote CO2 degassing. I'll talk about some examples of that. Different ways in which you might just change the available ion pool, so your carbonate saturation. Things like evapotranspiration or evaporation and what role that plays in supersaturating your fluid, as well as, of course, on land, a lot of strong substrate control. So is your lake kind of cored by a nice carbonate out west here, a nice Paleozoic limestone that can be dissolving and providing a big source of calcium and carbonate ions to your system? If you think about that even in terms of soils, what was that parent rock that soil is developing on, and what's that going to do to your carbonate saturation? And then, of course, the role of temperature itself. So we have, particularly outside of the tropics, we have very high temperature change throughout the year and on a daily basis. And so you can imagine that if we're just getting a mineral formation temperature, how temperature changes on land is probably going to dictate a lot, especially because calcite is one of those weird reversely soluble minerals. So as you increase temperature, you're more likely you're going to promote precipitation out of solution.